Okay, so this video is meant to go through two examples of induced EMF that are in your workbook. So this first one says a square loop of wire with a length of 40 centimeters experienced a uniform perpendicular magnetic field of 100 milliteslas, and the field goes to 0 in 0.01 seconds. What is the magnitude of the EMF induced in the loop? So just a reminder of our equation for induced EMF. Induced EMF is equal to negative n, which is the number of turns, times our change in flux over our change in time. And if I expand that out a bit, it's negative change in BA cosine of theta over our change in time. And when we're looking at this, this change, we're really just looking at what variable is changing. Is it the magnetic field, is the area, or is it the direction, or the orientation between the magnetic field and the area? So in the class, in the examples that we're going to do in our class, we're only going to have one thing changing, and so we'll just apply this delta to the one variable, and then we'll bring the other variables out. So in this case, our field is going to go to 0. So this means that our equation is effectively going to be negative n. I'm going to just bring my other terms out of that delta, so area cosine of theta, and then it's really just a change in magnetic field over a change in time. Okay, so let's just kind of figure out what we know. We know that this is the length. It's perpendicular to the magnetic field, and I know it says it's perpendicular, but kind of effectively what that means is we have this magnetic field that is like passing through it. And so that actually means that our angle is 0 degrees. Okay. And this is our initial magnetic field, and then it goes to 0, and that is our time value. Okay, so in terms of our equation, it's one loop, so the n value is 1. Our area is going to be, it's square, so it's going to be 0.4 times 0.4, that's just the area of a square, cosine of 0, times our B final, which is 0, minus our B initial, which is 100 milli, so times 10 to the negative 3, over our time value of 0.01. And a good student would pause the video, get out their calculator, calculate this out, and you should see that you get a value of 0.016 volts. Now notice, this comes out positive, okay? So the fact that it is positive means the induced magnetic field will go with the original magnetic field. So remember, if this is my visual here, if this is what it was, and let me get my lines. This is what the magnetic field looked like before, and now my magnetic field goes to 0, so now it looks like this. There's no magnetic field lines. I'm going to create an induced magnetic field, so it's a different magnetic field. I'll color it with green. My induced magnetic field is going to mimic the original, so this would be the induced magnetic field. So the induced current creates an induced magnetic field that is going with the original in this case. Okay, let's look at the next example, and the next example is a motional EMF one, so this is a very particular case. So it says a conducting rod is moved to the right on a U-shaped conductor in a uniform 0.75 Tesla magnetic field. Points into the paper, we've got these X's here. The rod moves with a speed of 1.9 meters per second, it's 30 centimeters long. So this is like my velocity, this is my length. It's got a resistance value of R. First wants to know, what is the induced EMF? So this is what we're trying to find. What's the induced EMF, the induced current, and then the external force necessary to keep the rod moving at a constant velocity. So if A equals 0. So the induced EMF is pretty straightforward because it is, for this case of motional EMF, the equation just kind of moves down to this BLV. So B is my 0.75, my length is 0.3, my velocity is 1.9. So that's a pretty straightforward calculation. And that should give you 0.4275 volts. And then to figure out the current, remember current is determined by the amount of voltage difference present and the amount of resistance in my conductor. And so I know that I'm inducing this voltage of 0.4275. I have a resistance of 2.5, so this is just going to come from Ohm's law. I is equal to V over R. So 0.4275 divided by my resistance of 2.5. Get out that calculator, and this should equal 0.171 amps. Okay, now in terms of the force, so there is this force that is like pulling it in that direction, but there is an opposing magnetic force in the other direction. That is what allows it to move at a constant velocity, because these two forces are opposite each other. And so according to Newton's law, if I have this applied force, nope, it's not B, where's my eraser? If I have this applied force minus the magnetic force, this should equal ma, but if it's not accelerating, this is going to equal 0. Okay? And that magnetic force arises from the fact that there is a current that is going to be induced in this wire, and we're shown in the picture that the current is going in this direction. And so you could, by right hand rule number 2, figure out, okay, if my current is going in this direction, it's going up, my magnetic field is going in, then you should be able to see that the magnetic force is going to the left. So my applied force just has to equal my magnetic force in this wire, and magnetic force on a wire is equal to BIL sine of theta. So my magnetic field, the external magnetic field, is still this 0.75. The current that is now flowing through this wire is 0.171. The length of the wire is 0.3. And the angle between my current and my length of my wire is 90. So that's going to be sine of 90. Oh, I have no more room. Ah! There we go. So we should be able to calculate that out, and I am going to leave this one as a, you calculate this out, and we will go over what that answer is in class, and maybe talk a little bit kind of conceptually if it's kind of difficult for you to grasp like the direction of that magnetic force there. Okay?